Hello, everyone. This is Michael McCool. I'm an engineer with Intel. And what I'm going to present today are two related topics on the IoT. The first is Web of Things, which is a standard that the W3C is working on to use web technology for a descriptive standard for IoT. And this technology actually enables something called semantic interoperability, which is a very valuable concept in IoT that I'm going to walk through the implications of. And so let's just dive in. A couple of new terms here, Web of Things and interoperability. I want to mention first the goals of the Web of Things standard is to support interoperability. The reason to have interoperability is to enable eventually something like an app ecosystem for IoT. So you want to have lots of different devices able to interoperate in arbitrary ways and be very flexible. And one way to do this is to use a well-developed existing ecosystem that does this, the web. So web services have been very successful and are very flexible and have really enabled a new kind of way to build applications. And so we want to figure out how to leverage our experience in that to build IoT service ecosystem. One of the problems, though, right now in IoT is that there are many, many standards for all kinds of things. And it's actually very confusing, and it's hard to know where to start. And things are also moving very rapidly. And some of these standards are actually necessary because of the wide complexity of different applications in IoT, but also some of them overlap quite a bit. And so when the W3C decided to look at what they could contribute to IoT ecosystem, they wanted to avoid replicating some work that had already been done or competing against existing standards efforts. So I'll explain as I go through this how what the W3C is doing is different and how it's actually complementary to a lot of existing standards efforts. Now the agenda for my talk basically is going to go through three steps: what, why, and how. So basically I want to talk about first what is interoperability and give some definitions so we know what we're all talking about. I want to talk about why it's important. Then I want to talk about how we achieve it. So what is interoperability? So basically that means you can kind of connect two things directly without any extra effort or adapters or whatever. And some examples are, obviously the web. I can fire up my web browser. I can go to a web server or website, and I get some stuff and I render it, and I don't have to do anything special usually. I might occasionally install a plugin, but most of the times the main content in the web, just shows up and gets rendered correctly, and that's fantastic. A lot of work had to go into standards to make that happen. Similar things, I plug in a device to my wall and then charge it, and all kinds of work had to go into standards to make that happen. In fact, there's even ongoing efforts on cleaning up charging, but it doesn't happen automatically. This requires some agreement between people, what voltages to use and what connectors to use and so forth. Similar examples are light bulb sockets, nuts and bolts. There are huge standards efforts for nuts and bolts, for example, in mechanical spaces to make everything interoperate, make it possible to order parts from multiple manufacturers and have them work together. So for the IoT, we want something similar. We have lots and lots of different manufacturers. And one of the unique things about IoT is that really it's impossible for any manufacturer to create all the kinds of devices we might use in all IoT systems. So we have to have interoperability to really achieve the goals of IoT, as I'll discuss later. And so for IoT, we want to use devices together in the same system. And we also want to share data between those devices, able to interpret that data to build systems like data analytics quickly and cleanly and cheaply. So that's what we want from interoperability, is we want to interface things directly. Now, a little bit more detail. There's actually different levels or classes of interoperability, and some of them we've actually done a good job of achieving. So, for example, I don't have it listed here, but communications interoperability, I want to be able to connect to a Wi-Fi system and be able to exchange data. TCP/IP. I might want to exchange messages over the internet. These are all standards efforts that have achieved data interoperability. But then once I have the data, how do I decode it? And so there's actually 3 levels of that, at least. I might have to, the data is a bunch of bits. How do I break that down into, elements of data? And so I have a syntactic level of interoperability where I want to, undo the encoding of the data and turn it into some internal data structure. So I have what's called a serialized representation, a sequence of bytes on the wire, and I turn that into some internal data structure like a tree. Structural is, I've got the data decoded, but I have to organize it into types, and I have maybe organizational patterns like lists or sets or arrays or tables or objects, etc. And I have some kind of organization or schema for my data. And so once I've parsed it at the syntactic level, then I have to sort of put into a schema, put into a database, and that's the structural level. But even once I have data in my database, I may not know what the data means. And so I may have, for example, a number in the database, but I don't know if it's a temperature or what unit it's in or what time it was taken and which elements of my data meant time and which the elements of that time was associated with the temperature taking and so forth. So semantic is I have a standard vocabulary or set of terms like temperature or units Celsius, degrees Celsius, and I can tag data elements with those elements. So I now know what the data elements mean in context. And so semantic interoperability is a very high level of interoperability where I can look at data and really figure out what it means. Now, if you do a search on semantic interoperability, you'll find a bunch of stuff, and there's actually more levels that people can consider. But I think for now, we'll just stick with the semantic interoperability level. And what's interesting is there's actually quite a lot of work and technology into expressing semantic interoperability in the web. So there's been work on the semantic web for a long time. There's some really interesting technology available there for doing inferencing between different kinds of semantics, for defining vocabularies and so forth. And so the nice thing is that's a pretty mature technology. We can leverage it for the IoT. Another thing worth saying is that when you talk about the IoT, it's not just the data and particular message that matters. It also matters the protocol. What's the sequence of operations? What are the APIs for web services? And so there's actually information in the structure of the exchanges and the sequence of exchanges. Now, one of the other things that has happened in web services is people have followed particular patterns for API designs to try and also make this easier to exchange. So 2 examples of such patterns are RESTful APIs and the HTTP pattern. And the idea of RESTful APIs is you have you sort of avoid modal interactions or things that imply state, that require state. And you have each interaction be meaningful in itself. And HTTP is using hypermedia so that when you get a result from an exchange, it tells you what the next possible actions are from that exchange. There's also a number of things with sequencing that happen to do with security. So you have to onboard devices, you have to figure out the identity of people, figure out where the data is coming from, who you can trust, et cetera, et cetera. And all these things have additional constraints on interactions. And so for a single exchange, though, you also have a payload for that exchange. And fortunately, it turns out the first level of interoperability, syntactic and structural, are also dealt with pretty well by things like JSON and XML. So JSON and XML are self-describing syntaxes. The parsing is straightforward, so syntactic interoperability is taken care of. And the structure of the data is self-describing so that you automatically get a data structure from the JSON or XML file. So this means we have a pretty good job, it's pretty straightforward these days to achieve syntactic and structural interoperability. Now, not everything uses JSON or XML. There are plenty of other standards out there A good example would be BACnet using the IoT, where you have to know that it's BACnet and decode it. But for the most part, these can be interconverted to JSON or XML. And so we can still focus on JSON XML as our primary medium of exchange, and that achieves syntactic and structural interoperability. It's also possible to give grammars and things, or called BTDs for XML, to constrain the structure, but it's actually optional in modern systems, and usually useful for validation. Okay, so that's kind of maybe more detail than we really need at this point, because before we go too much farther, we have to motivate why we want interoperability. So this is all, sounds very complicated, and why should we bother? So, and basically, it's the money. So there's a really useful report. You can look it up later, and I urge you to read it, McKinsey and Company. And they basically looked at what was the business value of interoperability. How much money is it worth? So there's been a lot of studies for the total value of the market for the IoT. And what they noticed, what they said is that in this report, they kind of assumed that the market would be interoperable, and that if it wasn't, you would lose 40 to 60% of the value of the market. So basically, the market would be worth in 2025 $6.5 trillion by their estimates without interoperability. But if you had interoperability, you would significantly increase the pie. And so the purpose of interoperability is that you can combine things and create new services that you wouldn't have been able to create otherwise. And those businesses don't exist without interoperability. So that's the value, is you create new opportunities by combining things from different manufacturers. So, and the mathematical reason for this is that when you have a network, you basically get combinations of things. And the number of combinations grows faster than the number of elements in the network. So, for example, Metcalfes Law, says the value of a network basically grows quadratically with the number of elements of the network, because that's the number of possible pairwise combinations. Now, that was sort of an idea of a phone system where you have pairs and only pairs matter. But what's actually interesting about services is that a service may include n things, not just two things. And so if you actually think about services that combine multiple entities, you actually get combinatoric growth as the number of interoperations rises. So the value is actually nonlinear with interoperability. So it's very important to get as many participants in the network as possible to get the maximum growth. And in order to really scale the IoT, we need to get this interoperability happening. Now, you'll notice here on the slide, I actually have some logos from several standards. And the goal of many of these standards organizations is, in fact, interoperability. So within a given standard, you have the devices that follow that standard will interoperate. So the next level above that is, how do we get devices that adhere to different standards to interoperate? So that's what I like to talk about, and this is where we get into the goals and purpose of the Web of Things. So basically, Web of Things is targeting inter-standard interoperation. Now, there's kind of, many of these standards say, well, all you have to do is everyone has to adopt my standard, and then we'll all interoperate. But the fact is, there are different standards for various reasons. They might have come from different backgrounds. Maybe some are medical, and some are home, and some are industrial. Maybe some do real-time control. Maybe some do RESTful APIs. Some do publish, subscribe, and different geographic regions. So there's a lot of reasons for having these different standards, and so we kind of are assuming there will be multiple standards for a while, and that we have to worry about this interoperation. So we want to figure out how to build systems that use devices that come from multiple standards. There are also two other reasons for worrying about multiple standards. First of all, there may be devices that follow no standard, that are just using existing technology like web service APIs. And so how do we talk to them? And then finally, there are devices that already exist, that are already installed and in the field and running, and kind of like legacy devices. An example would be BACnet, and how do we talk to them? How do we include those in future IoT systems? So if a city has invested millions of dollars installing lights, that have a certain interface, they're not going to rip those out and replace them with new devices because the standard is different. They want to figure out how to talk to the existing devices. So, and the fact is that IoT systems get installed and will be around for a long time. There's devices being installed today that'll be around for 20 or 30 years. And so it doesn't matter what standards happen in the future because those devices will still be there, still doing what they do. Maybe some can be updated, but for the most part, we just got to deal with devices as they are. And so, the idea here is how do we, get multiple standards to interoperate. So, anyways, Web of Things wants to enable interoperability. Now, the fact is, most standards, as I said, have this goal of interoperability. It's kind of what standards are for. So, and as I also said, the W3C didn't really want to butt heads directly with these other standards because there's already lots of them. So what can W3C do that was different and that would contribute to the overall ecosystem in a productive way? So we decided to take a different approach, and I'm actually co-chair of the W3C Web of Things working group. So I take a different approach. So most standards prescribe how devices should operate. They'll say, here's a set of rules, and your device has to follow these rules. And very often, a standards organization will also say, submit your device to our testing system, and we will verify that your device meets all the requirements of the standard. And if it does, we'll let you use the logo, etc. And then if you buy a device that has been validated against the standard, you have a good chance of it interoperating well. Okay. And that's the prescriptive approach. So Web of Things decided to take a different approach, which is descriptive. So the idea is there are devices out there. They've already shipped. They're already in the field. People did the interfaces the way they did them, and they might have used some standards like HTTP or MQTT or something like this, or OCF or OPC, but they're already out there and they shipped. So rather than trying to validate devices in advance so they interoperate, what we're going to do instead is describe how the devices work and what their interfaces are. We're going to describe their interfaces so that other devices can figure out how to talk to them. So the approach is kind of like the reverse of prescriptive. It's actually complementary because many other standards also need ways to describe how they work to each other, even within their own ecosystem. And so having a good way to describe the interfaces for devices is actually useful even within a single standard, but it's especially useful between standards. So the technology used is basically by creating a standard for metadata. So the metadata basically describes the interface to the device. What API calls are available, what network transactions are supported, what transport protocol should be used, what kind of security metadata you need, et cetera, et cetera. And so we describe this metadata for a given device, and then if an application wants to talk to another application, another thing, it can read the metadata and figure out how to adapt the interface. And the terminology that we use within the Web of Things standard is you write a thing description for a thing. And so the thing description is the main deliverable of the Web of Things standards effort. And it's basically a simple file that includes a bunch of metadata about a device that describes its interface. And it's actually based around an abstraction that you have actually three things. The important thing here actually is properties, events, and actions. So there's kind of like an interaction model which supports properties, like a stateful thing that you can set and get and observe. Actions which you can invoke and that can conclude, and events that can send notifications. That abstraction maps to many different standards. And so the idea is you work with a thing description at this sort of higher level of abstraction, and that maps down to a concrete implementation for a given standard. We also have this idea that we can annotate things with semantic data using the W3C's linked data semantic framework. And that allows you to hook in to semantic processing and semantic reasoners that can help you with interoperability and with things like semantic search that I'll explain later. So basically, the deliverables from the actual standard, the number one deliverable is, of course, the thing description, which has these properties, events, and actions, and is encoded actually in a JSON LD file. I'll give you an example in a minute. And then there's a few other things that are also included. One are some set of parameter templates that can express how a given thing can work with different kinds of ecosystems, different protocols, CoAP, HTTP, OCF, etc. And we also define a scripting API so that you can easily write a script that can pull in the thing description and then give you a simple way to interact with the devices using like get and setters on properties and so forth. And so the idea is a kind of a browser-like environment where you can download a thing description like you can download an HTML page. And once you get that thing description, you can then talk to the device it comes from easily. I should mention, too, that thing descriptions can either come from objects directly in a kind of smart object self-describing framework, or it could come from the network somewhere. So if you have a device and you know who made it and you have an identifier for it, you'll be able to search a database on the web somewhere to find a thing description for it. So a device may or may not know that it can be accessed by a thing description. So for new devices, they might self-serve their own thing descriptions. But for existing legacy devices, you would probably take a second approach where you simply find the thing description about them in a database online somewhere. So either approach is fine, and the second approach allows you to pull in legacy devices and also devices that don't necessarily weren't designed to work with other things, but we can still, after the fact, write a thing description for them. And just to be more concrete, and I know this is a lot of code to throw up on the screen, but just to give you an idea what it looks like, this is a thing description example, and it's actually for an OCF device. And it actually is a demo called the Smart Home Demo that Intel put together that basically runs OCF devices in software as a test case. And I can run these on the network. And actually, I wrote a program that I call a metadata bridge. It actually reads the existing metadata for OCF devices, introspects them, and then automatically generates a thing description for them. And so then you can actually work with the thing description and talk to the OCF device, not even knowing necessarily that's an OCF device. And likewise, you could write similar metadata bridges for other kinds of ecosystems to convert them into a common normalized metadata format. Now, the other thing that's worth pointing out here, in the green, in the red, we're actually using semantic web technology. So the green lets us specify the vocabularies we're using to refer to semantic elements. And the red lets us specify semantic categories or statements about the thing interface. So what we have here basically is we have a light, okay, and the light has a property which is its on-off state, called the switch status. And basically it's a Boolean, and we can set and get it to turn the light on and off. Pretty straightforward. But we have some semantic categories here so that we know it's a light, and there's a light control, and it's an actuator, so that we can do things like search for all lights in a room, and then also search the interfaces to find out where's the control to turn the light on and off. So we can sort of automatically search for things to do this. And in fact, there's even, I'll show you in a minute, a system for doing this. So, and actually within the individual payloads for how do we structure interaction with the device, there's sort of an embedded schema that you can actually describe the payload that you use to send data to and from. And within that, you actually say how the data is formatted and give some additional semantic tags. So lights actually come in different forms, and let me talk a bit more about this too. You might have a light that's just simply on and off. You might have a light as a brightness, where you give it a number, how bright it should be. You might have a light that gives they take a color, and colors could be in different color spaces, HSB, RGB, etc., right? So how you actually turn the light on and off actually can vary from light to light. So it's not enough to just know it's a light. It's not just enough to know what is the API entry point for turning light on and off. You also have to know how to structure the data to create a message to turn the light on and off. And so each of these levels of semantic categories, this tells me it's a light. This one tells me this is the API entry point turning it on and off. And finally, this tells me how to structure the data to actually give it an on-off message. And there are many subcategories in each of these levels. So anyways, we can take this thing description and besides just stating the raw information about the protocols, we can also give the semantics. I should mention, however, I'm going to talk a bit about semantics, but there is some concern in some communities that semantic processing is too heavyweight for IoT. So there's two mitigating factors, however, and we've taken this into account in the design. First of all the semantic tagging is separated out, and you see these @ symbols. Semantics only appear in things that have @ symbols, and @ symbols can always be ignored, and you still get the basic information about the device, about how to talk to it. So if you already know how to talk to a device, this will give you the information you need for like JSON schema type information. So you can basically ignore the semantics if you want to. And also, the smaller devices are typically just providing data. They aren't processing it. And so small devices don't need to understand the semantics. It's more the consumers of the devices, which typically live in the cloud or in gateways, which are more than capable enough to be able to process the semantic information. So in two ways. First of all, you can just treat this as a JSON file, which is very easy to parse. For small devices, you can ignore the semantics. But for more complicated devices, it gives you many hooks to be able to do more sophisticated things. And in particular, it's perhaps not really clear, but these semantics are not just simple strings. They're actually terms that are related to each other in a vocabulary. And there's a technology called RDF, and also it can be expressed in called JSON LD, that let you express relationships between lights. So I can express relationships with different color spaces, for example, or between color and brightness, or between different units, or I can say what units make sense for temperature, or I can say that a thermostat has a temperature sensor and an actuator. I can say various things to be able to reason about the relationship between different devices. And so it's not just a simple string tag. It's actually, first of all, standardized strings. So there are strings that have known meanings that everyone agrees on, and they're also related to each other. And you can use the relationships to infer things about them. Now, many standards use standard vocabulary, and very often it's defined informally. The advantage of JSON LD is it makes the vocabulary formal. So you have a computer can now process the relationships and can follow those threads of relationships. And it's also explicit, so that you have encoded it down in a standard way, and so it limits the problems with ambiguity. And there's a bunch of stuff out there that tooling, and the tooling can be used in various ways. One way it can be used is just for validation. So you can just make sure that everything is related in a reasonable way. But one of the things you can do is do search. And let me just pull up a page here. So this is actually an open source project on GitHub. It's called the ThingWeb directory. And this is actually an open source project that goes along the Web of Things. And basically what this does, it's a service that things can register thing descriptions with. Thing descriptions go into a database. And it's actually a semantic database that is searchable with a query language called Sparkle. Sparkle is kind of like SQL, but it can search semantic relationships. And you scroll on and find an example here. So basically, you can do a query, and so here's like a URL going to the service, and the query, has X, Y, Z. So RDF basically uses triples of entity, relationship, entity. So I can say Shakespeare was a writer, and now I've related, Shakespeare entity to writer category. And I can make various queries like this and conjunctions. And I can search for things that satisfy certain constraints, relationships and other things. I can also do simple searches and or conjunctions and so forth. So I could say, all lights that are in the kitchen or things like this, right? And so you can look up things by certain properties. I should mention actually that all terms in RDF are actually given URLs. You can actually follow the URLs to see them. And actually, I'm using a terminology called IoTschema.org, and yeah. So, anyways, if you go to the site, you will see that there is a vocabulary. Actually, there's a larger site called schema.org that looks at vocabularies for all kinds of things, and IoTschema.org is particularly looking at schemas for IoT. Okay. Anyways, each of these elements has a URL, and you can dereference to find this. So, anyways, Sparkle is a standardized query language. You can do these queries that can be used for discovery and for finding sets of devices that satisfy certain constraints. And you can put in all kinds of domain information about those devices. And there's a whole set of technology that can do that. Now, IoT.schema.org is working on coming up with a standardized terminology for IoT. You don't have to use IoTschema.org for Web of Things devices, but they're definitely complementary efforts, and that having a standardized schema that everyone agrees on is convenient. But the nice thing about RDF is you can actually relate multiple schemas if you had to, and so it's something that can evolve over time. And it will evolve over time as people come up with new kinds of things they need to talk about. One of the things about IoT is constantly evolving, new kinds of devices being created, new kinds of sensors. We have to have an open-ended system. So we see here kind of some relationships between where schemas belong and where things like metadata and systems like OCF belong. And so the IoT.schema is focused on defining schemas and common vocabularies to allow you to talk about things in a common way. And you can later look at these links. I also want to mention one more thing about the idea of how IoTschema.org structures things. It actually doesn't try to define categories for individual devices, because actually devices are pretty complicated, and different kinds of devices from different manufacturers can be structured in different ways and have different capabilities, different things they can do. So actually, IoTschema.org defines something called a capability, which is something that a device can do. But any given device will have a set of capabilities, and its overall interface is actually the union of all the different interfaces for all its capabilities. And so things are more like bundles, and the bundles are these bundles of capabilities. Each capability is a certain interface, and you're basically doing, I guess, called a mixing class, where you mix together all the different interfaces for all the different capabilities. And this is more flexible because that means you could have, for example, an air conditioner with a camera or whatever, right? So you can combine multiple capabilities into a single device. Right, and I think one very important thing to say here is that we can't just treat semantics as picking things from the list. You know, people are inventive and they will create new kinds of devices and they want to describe them. So we need a system that says model devices, not just select them from a list. And so the idea of the semantics is anybody can add new meanings or new terms to the ontology over time. And you can immediately publish and use a semantic vocabulary in a thing description. And as long as you make your definitions public, other people can use them too. So this IoT.org is trying to establish a structure for how to enable this to happen, and also a basic foundational set of vocabularies. So that's basically my talk, and I just want to summarize the few points here. First of all, interoperability has significant business value generally, and it has particular value in IoT. And the reason is that no single company can possibly invent or deploy all the devices used in IoT. And many of the most interesting applications of IoT must involve devices from multiple companies. So we have to deal with the issue of standards to do interoperability. I described the Web of Things approach that uses a descriptive approach for interoperability rather than prescriptive. I do want to say that prescriptive standards definitely have their place. And there are places like security where you want to say how devices should operate. And you do want to validate them against that standard to make sure they have good security, for example. But in their case, there are also many places where devices can do different things, and there's no particular reason to do one thing or another. And it's really hard to get people to agree on those kinds of things in a standard. So the descriptive approach simply says for those kinds of things, we can just describe after the fact what the device does. And we standardize as much as we can, but the descriptive approach gives people the freedom to innovate and do new things in their interface without having to, go to a bunch of committee meetings to decide on who does what. The main deliverable from the W3C, Web of Things Working Group, is the sort of universal metadata format for IoT services. And so this thing description is a JSON LD file that describes things. You can interpret this as a regular JSON file if you want, and then you can just read out, what are all the links and things you need to talk to a device. But you can also put it into a semantic processor and do semantic search and reasoning and figure out which devices work together and which ones are related and which ones are in the kitchen and all this kind of thing. So it also connects to the semantic technology, which is extremely powerful, and I think there's many, many interesting applications that we have yet to explore to use this technology for IoT. But I do want to reemphasize that small devices do not need to deal with the semantic technology. It is something that is an optional feature. That is something that if you want to do search and so forth, it's more of a server-side or cloud side system, not device side. And we're striving actually to keep the device side requirements as low as possible. So with that, I'm basically at the end of my talk. And I just want to maybe point out one final thing. If you're interested in reading more, the Web of Things has published some first public working drafts. The goal of the standard is really by the end of 2018 to have a candidate recommendation. This is still our first public working draft. And so the other companies working on the standard are Panasonic and Siemens and RWE, and also Samsung, SmartThings, and there's a long list. You can find out who's been working on it by following GitHub. And if you want to participate, you're certainly welcome to join the working group. And you can also give feedback through GitHub issues on this. There's a lot of this stuff here about different scenarios and use cases, and different kinds of ways in which we might want to use things. And I don't have time to go through all this, but you're certainly welcome to contribute to this. And we're trying to figure out, all the different scenarios. We actually have plugfests many times a year where we try to get devices to talk to each other and to work together. And in addition to sort of this overall document, you can also follow links, if I can find them here, to, for example, the thing description document. Let me find the actual released version. And here you'll see a lot more information on, what a thing description looks like and what's in it. So with that, I can take questions on the chat, I believe, and I'm happy to stay around for a bit and answer such questions. Yeah, and actually, I almost forgot one more thing I should say. I showed you the thing directory while waiting for questions, but you also go to GitHub and you search under W3C. Actually, sorry, search for NodeWatt. Yeah, this is actually an open source implementation of the scripting API and thing parser. So this is another open source project. In fact, we have a submission to the Eclipse Foundation for both the thing directory and for NodeWatt to be under Eclipse. And both Siemens and Intel are working on this together, as well as other companies. And we're primarily looking at Node.js right now, but eventually we hope to also expand the API to other languages like Java and Python and so forth. If anyone wants to contact me, I'm sure there's a way we can set that up. So with that, I think I'm going to close the conference, but thank you very much for listening.